Hello. Welcome, everyone. I wanted to start by thanking you for coming to the first seminar of the semester of the MIT Robotics series. And I wanted to thank Matthew for donating your time and effort to come here and visit and give us a talk. And especially wanted to welcome, I don't know if there's anyone in the audience that this is your first semester at MIT. If you are here, I wanted to especially welcome you, right? This is a seminar series and MIT Robotics and many of the things we do, this is for you, right? So welcome to what hopefully will be your home for a long time. Anyway, yeah. Hopefully it will be a home that you will get to enjoy, where you will get to sort of chase your dreams. Matthew, as I was saying, thank you for coming. Matthew is an associate professor at Michigan University in many departments, Naval, Marine, EECS, so a lot of interdisciplinary work, as it's usually the case in robotics, which is cool. Matthew is a very well-traveled person, did his PhD in Sydney. I don't know if you might be able to get it from a stint in your accent. Then postdoc at KTH in Sweden, and then now faculty in the US. So very broad spectrum of experiences. And he will talk about robotic perception in the field. And one of the anecdotes that I like is that he was driven into this field, into this research, because of the first DARPA Grand Challenge, trying to make cars drive at high speeds in the desert. And where, if you think about it, it sort of gives you an idea of why he was sort of inspired to continue working on robust perception, to get robots to do real things in the real world. Anyway, thank you for coming, and please.
Thanks. Well, thank you so much for having me. I'm really excited to be here, and thanks for inviting me, you guys. So to that point, I'm going to hopefully talk about some things that get to this idea of how we would translate a lot of the things that are happening right now in perception more broadly into the field, and sort of where that interface is between robots, particularly robots that we want to have out in the field. So field robots, big sort of outdoor robots, and sort of where perception is going. So nowadays, if you think about perception, so much of it has become dominated by this idea around deep learning. And so I guess some of the work I'm going to talk about today is sort of how we're trying to think about where the gaps are in between where deep learning is and sort of where computer vision is as a field, or deep learning outside vision, and where we are in robotics. And so, and this was sort of unthinkable even sort of when I was an undergrad and in grad school, this idea that we would get good enough at identifying things in still images that you could have sort of image retrieval work at sort of robust levels. And so this is sort of the canonical example now of where deep learning is, that I can show you a static picture and, with some level of accuracy, say what things are, right? And I think it's something that we take for granted now, but I do want to kind of give the historical perspective that if you talk to people that have been around for a long time, this is a huge step forward in what is possible in vision and in passive perception in general. And so that is really, really cool. So everything I'm going to say today is not that none of this works, but that perhaps some of it maybe needs to be rethought, or we need to think about where that sort of approach kind of intersects with robotics. And so, the kind of, again, the canonical example of how this works, this slide I stole from NVIDIA, right, is you have a bunch of training labels for a supervised problem, cars, buses, trucks, motorcycles, whatever. You train them in your deep net, and then you perform inference with it, right? And this has become something that we're all really familiar with because it is blasted at us through many different channels, and the popularity of those fields have become really, really immense. So I think it's important to acknowledge that sort of that is sort of where a lot of the research has been going. And so, really specifically, I'm going to talk about two kind of field applications. One's going to be driving, the other one's going to be underwater robots. But you can imagine that the first thought you would have as to how to apply this, right, is you're going to say, great, well, I'm going to run that thing that worked on static images. I'm going to run it on images I take from a robot, and I'm going to say, things that would be robot relevant. So in this case, people, cars, helmets, motorcycles. So not just birds and ducks and trucks, et cetera, but things that are relevant for the robot. But I guess if we get to the crux of that, right, is that the right answer, and is that always going to be the right approach? And I think it was the first approach people took. And the question is, how do we kind of move beyond that, or what are the limitations of that? So people have been developing more, and I guess I would argue more sophisticated problems around that, moving beyond just bounding boxes or static image classification to per pixel classification. And again, you can imagine why that would be useful for a robot. But if you get down to the core of this, right, it's not immediately apparent how a per pixel segmentation is immediately actionable, right? It's actionable for certain tasks that you would have for, like, let's say your Facebooks or your Googles or whatever, but it's not immediately clear how you would use this to take action in the world. How do I move through this space? Particularly because this is in the image plane, and so all those decisions I'm making are in 2 dimensions. And if you look at the accuracies or even the performance of these things in kind of full 3D space, you see this big drop off. And so again, classical vision has been, or not classical vision, but modern computer vision has been focused on these problems, and how do we make that work? Probably most importantly, I think, to think about where the weaknesses or where the limitations of this are around the way that we get to those things. So if you look at this, the way that is actually produced is through really, really laborious hand labeling. And so there are a bunch of data sets that have been produced that we now use and we think about in robotics as sort of ways of solving these problems, but they come on the sort of backs of very intense human labeling efforts. And one of the most important things to think about this is not that necessarily, well, there's some ethical and moral questions around whether or not this is the right things that humans should be doing, but most importantly is just that the scalability of these approaches is quite limited, right? Even if you're willing to dedicate large amounts of human resources to labeling, you are still quite limited in the number of scenarios, types of data you can label. But most importantly, if I get new sensors, if I get new environments, if I get new whatever, if I have to repeat this process where I have to put 100 people in a room, where they spend 10, 20, even up to an hour labeling an image, the question is how scalable is that in the long term? And is that the right thing for robotics, particularly when we operate in a much wider range of sort of scenarios and environments than would be sort of applicable for your Facebook, label your friends, Apple images, et cetera. And just to give a sense of what it actually means to do this task, this is what a human has to do. So they have to go through, and I've actually done this with my graduate students for a project. It was incredibly unpleasant. It took over an hour per image for me, and I don't know if I'm sort of the median or whether or not there are people that are faster or slower, but it was really, really boring. And I did like 10 images, and I was like, this is for the birds. And so what this really gets to is this sort of division that I see. So I like to work on these type of platforms down here. There's a bunch of vehicles. I'll talk about a few of them a little bit in the talk today. But this division between what has kind of risen up, and ImageNet is, again, I would argue, sort of one of the jumping off points for a lot of this, where we had a large labeled image data set. And then we were thinking about, OK, well, what can we do with that? People have done really amazing stuff with that data, but what is the division between that and the type of robots that we'd want to deploy in the field? So these are some robots that we've used. I'm also going to talk a bit about self-driving cars and applications in that, but we also have fetches and other kind of humanoid robots doing grasping manipulation. And the question is sort of where is this gap between what the computer vision community is doing up here and what we're interested in doing down here in robotics, from the perception standpoint, obviously. I talked about sort of what it takes to think about perception in these contexts, but I spent a lot of my time, and in fact probably an inordinate amount of my time, just working on deploying robots. And so luckily that, for at least underwater robots, all the big companies haven't dumped a bunch of money in to compete with me, and there's not a bunch of Googles and Facebooks of the world trying to deploy AUVs. So we have a lock on that market for a little while, but these are the typical vehicles that we use in my lab to take image data. And so we have downward-facing cameras on them. You can see them maybe there. Oh, they're a little hard to see. But we're using traditional machine vision cameras. They're very similar to cameras that would be in your cell phone. And we have them downwardly facing, and they're swimming around taking pictures. We're also using the fetches. We put cameras on bigger robots. This is one run by the University of Rhode Island, so that we have a downward-facing camera set that we have some data on from there. And this is what I spent my thesis working on. So this is an AUV developed in Australia. Well, actually, sorry, developed at Hui, which we then modified in Australia and built some downward-facing cameras on and took a bunch of camera data. So the long and short, I guess, of sort of the arc of what I want to tell you about is there's lots of ways of gathering really rich camera information from robots, particularly underwater robots now, and also obviously cars. And so we've been lucky enough to have a research lab with Ford. They've lent us several of these vehicles. We've kind of outfitted them with a bunch of additional cameras, and so we're able to now gather huge volumes of data. And so this sort of notion of big data, or whatever you want to call it, we're sort of there with robotics now, right? We can gather huge volumes of really, really rich camera imagery at whatever rate you want. That's sort of where we are now. And the real challenge, or the real thing we don't have access to, is massive amounts of human labels. And so how do we bridge that gap? How do we use the data that we have more intelligently, or how do we get away from having to label data itself? To give a little bit of history of the stuff that I like to think about when it comes to self-driving cars and why maybe they don't work right now. If you think about from like the early 1960s, there have been sort of self-driving car projects that have been around that have done sort of lots of interesting things. So there's an RCA project where they had metal cables installed in the road and were able to drive only lateral control, but fairly credibly, even as far back as then. There are a number of projects at universities and other places. I would argue probably the kind of pinnacle of it being the Nav Lab 5 in the 1990s, and that vehicle drove all the way from Pittsburgh to California. And again, arguably doing the same thing that sort of a Tesla autopilot is capable of doing. And so one of the reasons why I think we see this big gap in where we are now and sort of what the challenges are still facing self-driving cars is that a lot of the things that we think of as being credible systems that are really out there doing a lot are doing things that we knew how to do a long time ago and then kind of stopped because we hit a wall. We realized, okay, well, this isn't going to be deployable more widely. There's been a huge injection of money, but that doesn't seem to have gotten us over that hump. And so we'll see what happens. I got in much later in sort of the early 2000s on this vehicle. But there was sort of this arc in increasing sensing modalities, better sensors, certainly better, more sensors and higher volumes of data with kind of greater levels of fidelity. But I think one of the challenges is we still don't have a way of taking that data, interpreting it, and turning it into something that is actionable in a way that is always safe. And so it is not the volume of data that is limiting. Again, it is thinking about the way that we interpret or use that. And so again, it comes back to this idea of, is it just hand labeling more of this, or are there other ways of getting around that? The last thing I'll say, I guess, on self-driving cars before we kind of jump into some of the more technical material is just that we may be somewhere on this hype curve that I stole from some firm that probably makes a lot of money doing this. But the idea is that, one of the things I hope that certainly younger students take away from this, right, is that there may be some backlash that we are approaching on certainly level 4 or autonomous cars that don't have people in it. And I hope that some of you stick around in this and keep working on it, because I do think we've come quite a long way from where we were, at least in the early 2000s when I got started on it. And it would be a shame to see a lot of that effort not be continued just because it hasn't worked out as quickly or as efficiently from a capital perspective as people wanted. And again, a lot of what is involved in self-driving cars, I use this image. This is all LiDAR data that's being labeled. I believe this is in China from a New York Times article that was talking about sort of some of the human costs of doing a lot of this machine learning work. Okay, so that's a lot of naysaying. So what are my suggestions as to how we would get out of this? So I'm going to talk about a couple different ones. But some of the ways that I think we can avoid this trap of continually labeling additional human data is thinking about physics and simulation. There's a lot of people doing really great work on that axis. We'll talk about motion, which is an inherently robotic thing that doesn't exist in your image retrieval task. We'll talk about multiple sensors, cross or self-supervision. And then finally, a bit about domain adaptation using some of the data that we have in a more smart way. Okay, so physics and simulation. So I was a PhD student, and then I was an assistant professor or postdoc and assistant professor. So I had no time to play video games, and in the intervening time, video games got great. And so one of the things that really amazed me when we started looking into this is just sort of how far graphics or photorealistic rendering engines had come. So this is Grand Theft Auto, which a couple of years ago we spent a bunch of time trying to get data out of just because it was sort of the most photorealistic simulator that we had access to. we were quite afraid that we were going to get sued by Rockstar Games. It was us and another outfit that were trying to basically grab data from this. We called Rockstar Games. We were like, hey, do you guys want to work with us? They were disinterested. We did not get sued, and now enough time has passed, I don't care anymore. But one of the things that having a photorealistic simulator really enables, right, is the ability to do this idea of domain randomization. So if I take the same scene and I permute many of the photorealistic properties of it, you can use the same labels that you're automatically able to get from the video game, but think about having a network learn invariances across these different photo properties, right? And so this is the same scene lit in a variety of different ways. And so what we ended up doing is actually hacking into the game engine, running one step of simulation of the game time, then cycling through all of the weather conditions, light parameters, everything else that we could do in that game to kind of vary the visual properties, and then feed that all directly into a neural net. And so you can see that they have some degree of volumetric rendering. There's some weather conditions. You can vary those kind of things. I'll save you the details. It is incredibly difficult to get any data out of this. It was a huge nightmare. It breaks every single time they update the game. I would not recommend anybody pursue this. People have started to produce better simulators now, well, other simulators now. Tragically, I don't think anybody's really matched the photorealism of Grand Theft Auto. So there are some new ones now built around the Unreal Engine. There's a bunch of commercial companies. But long and short of this is that if you take this data, you take the labels from it, and you pump a bunch of it into a simulator, really the only win you get is by using a lot more data. And so we looked at cityscapes, which is about 3,000 images, the common data set used for autonomous driving. Kitty is 8,000 images, or at least it did at the time of this. And we generated 1 million simulated images and pumped those into a network at great grad student and cloud time costs. But the long and short of that is that you can actually end up doing reasonably well, particularly if you think about cross data set classification. So what you're seeing is object detection of cars on the Kitty data set if it was trained on cityscapes versus trained on simulated data down here. And basically, Kitty divides it up into 3 different types of cars. It's not super important, but the long and short of the story is the more simulated data you use, the better you can do. There's an asymptote there, and I think probably the more interesting outcome of this work was just that you hit some limit. Basically hit the limit where you've gotten all the information out of the simulator. We went from 500,000 to 1 million to 2 million to 5 million images, and you don't see any greater performance, right? So whatever information was contained in there, the network is keyed into whatever is useful in that, and then everything else you're adding is really just adding noise, and it's not adding anything useful. So I have a graduate student, Alexa, who's been looking at trying to use that simulated data or think about sim to real in some ways and try to adapt that data to be better for network learning. And so one of the real goals of that work was thinking about what do we know about how cameras work, what do we know about the physics of cameras, and can we apply the physics of those cameras to data itself. And so we know things about chromatic aberration. Those are effects of the camera lenses. We know that lenses often apply blur, certainly in the extremes of the lens. We know some things about how the camera sensor actually takes photons in and turns them into pixel values. So you can play with the limited exposure range that cameras have, some degree of sensor noise. And then, to be honest with you, a hack on top of that where you kind of just shift the color around to kind of fill out the domain randomization problem. And so what that looks like in the end is that you have real images from, let's say, Kitty and cityscapes, and they have a tone to them, or they have a look to them that if I showed them to you, you could immediately recognize it and say, oh, that's from that data set. And there's been lots of work, great work done here on sort of the data set bias that exists in these things. But if you look at simulated images like Virtual Kitty, which is a data set that matches Kitty exactly, but just puts it in this sort of artificially rendered realm, or even Grand Theft Auto, they don't look like real data. And so this was sort of early work in thinking about how do we take this physically based model and apply that. So what you'll see is sort of the domain randomization of that simulated data. And it still doesn't look real, but the performance gains you begin to see by even performing this domain randomization where you're kind of flipping up the colors, changing things, making it look less like a sort of artificial setup and much more I guess less artificial to some degree, begins to sort of buy you something when it comes to training these networks. And so it helps you at least get over some of this asymptote that happens when you're training on lots of simulated data. The thing I will point out here, and the other thing we learned from this, is that there's a limit to this as well. So we still are unable to match the performance of extensive amounts of real data. And it's not clear whether this approach will ever get to that point. But I do think that sort of the early things that we have learned is that it's really important to have a physical model of what your camera is doing and think about how that physical model of the camera is applicable to whatever synthetic rendering process you have. So here's an example. The red squares you're going to see here, this is going kind of fast. The red squares you're going to see here, oh, my mouse is really tiny. The red squares you're going to see here are examples of misdetections when you just trained on the simulated data or the simulated data combined with some real data. And then if you apply that augmentation, it's able to recover some of those misses. But this really gets to some of the important points when you deploy these things. You're still missing significant amounts of cars. I mean, obviously not always. As you get closer, you tend to get better. But you can see for a single shot detector that's just trying to make individual decisions about is this a car or not, we're still kind of nowhere near where you would need to be to have this be sort of the only system you had in a safety critical system. Okay. So sort of extending on that work and thinking about that in the underwater domain, I had 2 other graduate students, both of which have recently graduated, that were thinking about, okay, can we use a physics-based model of what we understand about how light propagates? So in that same way that we were thinking about cameras, but thinking about this in an underwater context. So why would that be an important thing? Why do we care about that? Well, we deploy camera systems like this on big underwater vehicles. So this is the Sentry vehicle. We built that camera system with my postdoc advisor. This is that URI vehicle. We built a camera system, again, in Australia and put it on there. But what we tried to do with that is build big 3D reconstructions, and this is sort of lots of my earlier work, again with my graduate advisors, on building big 3D models of the undersea environment by taking those cameras around and taking pictures. And the first thing you'll notice is that you'll see these, well, maybe not the first thing you'll notice, but you'll see these sort of light and dark patches that are on there that actually aren't real. So those lines you're seeing there are effects of camera attenuation, not really effects that are on the bottom. The other thing you'll notice is like stuff underwater looks crazy. These are bacterial mats at almost 1,000 meters off the west coast of the United States. But again, you can see these patterns, these sort of stripes and lines, and it's a little hard to see, but you can see these stripes and lines here. Those are not real effects. Those are not actual, there you can see it better. So those are effects of the vehicle and effects of attenuation of light and water. We also built big reconstructions of shipwrecks. This is just one I think is cool. These are a bunch of amphoras in a wooden ship that sank off the southern coast of Turkey like 1 million years ago, which is not an accurate figure. But long story short, we know what the physical process of light and water is. There's been really great research done on that. We understand how that works. And so can we use that to take data and then modify it to be better or more accurate or more actually reflect what we're really seeing? And so if you're thinking about image formation, I will kind of run through this really quickly because it's not super critical. But we know some component of it is direct transmission. So that is how far away is that object. So it's the distance along the line of sight. What wavelength is the light? So that means that things in the red spectrum attenuate faster than green or blue. What is the attenuation coefficient of the water? That's a thing that you need to estimate. So that's one of the challenges here. What's the radiance of the source? And then what's the viewing angle and what's the ray direction? Another component of that is scattered light. So the rest of that is energy that is thrown back into the camera. So it leaves your strobes, the sun. It hits particulates in the water, and it comes back to the camera before it hits the thing you're interested in. So there's a big component of that. This is a really well understood formulation. The challenge is not, do we know how light propagates or do we know how to measure these things? It is, how do you estimate the parameters of this function online? Or how do you estimate them for some body of water? Or how do you estimate them in the long term? And so we did lots of work sort of maybe 5, 10 years ago trying to figure out if we could do this in a more traditional way using sort of nonlinear estimation techniques. It ended up being very, very hard to do this robustly. And so now, sort of in the era of having big nonlinear function estimators that everybody's excited about, aka deep learning, we've been able to do a fair bit to advance where that was using those exact same models and injecting the physics understanding we have of how light propagates in water back into the way that we actually estimate these things online. And in this case, we use sort of the du jour technique, generative adversarial networks. But let me walk you through just in general sort of these students' work. So the kind of key here is we wanted to make sure that you could leverage something that we had easy access to. The thing we have easy access to is air data with range maps. And so there's tons of in-air data. Take a Connect, you wave it around. That gives you an in-air RGB image and an in-air depth map, right? Connect does not work underwater. As the first thing people ask me, why wouldn't you just use that underwater? It doesn't work. I can get into that why, perhaps offline. But long story short, we have tons of in-air data. And so what we would do is we would take that in-air data with the Connect map associated with it. We would use the propagation of light in water, which we understand, to render a version of that image given the depths of it as if it were taken underwater. Now, that's not going to be super accurate, but that doesn't really matter because what you're trying to do is actually learn the function of that for your water data. And so what the GAN piece of this allows you to do is allows you to take this RGB data set, RGBD data set, and your real underwater images. So I just gather as many real underwater images as I can. I don't need to label them. I don't need anything from them. And then what I'm attempting to do through this adversarial process is produce the function that would give me images that look similar to my real underwater data, by which I am learning the parameters of the data that I'm seeing now. And so as opposed to having labels or depth data that is accurate for the underwater data I have, I can use the aerial data along with huge volumes of underwater data, which is obviously almost free to capture once you have your robot. You can ask all the grad students that built the robot if it's free to build the robot. It is not. But that process then gives me the ability to take that, produce underwater images, and then I can train a separate network to then invert that process to give me images as if they were taken in air. OK, that was the slides of this. I don't know if everybody's familiar with this, but like a 2-second explanation of how generative adversarial networks work. So how am I comparing the two pieces of data? Right, so I have a generator network that takes some input data and produces fake data. In this case, it was the rendered underwater images using the physics model. I then have a separate network that is trying to decide whether the data is real or fake, and it has examples of real data and it has examples of fake data. And I obviously have the labels for that because I know what I produced and I know what's real. Through that process, I can iterate and get better at producing fake data and get better at discriminating between fake and real data. OK. So how does that work with the actual physics of this? What we do is we actually take in the same noise vector you take in a traditional GAN. We take in depth maps in the same way that we would have from the aerial data, in this case, the RGB image. And then I have physical models of all these things. I have physical models of backscattering. I have physical models of attenuation. I have physical camera models. And I can use all of those, learn the parameters of those online, and then produce my simulated RGB image from air. Compare that image using that same discriminator to real RGB data taken underwater. And so the attenuation model looks like this. You can refer to the paper if you're more interested. The backscattering model, again, can be composed of several convolutional filters and some noise. But I put all that together, and then I end up, again, with a synthetic RGB image and a real RGB image that I'm comparing. And at the end of that process, what I really want to do is take that, back it out to a depth map, back it out to an RGB image, and then produce an image as if it were taken in air. And so again, the kind of end process of this is I can take underwater data that I have no labels for. I can learn the relationship between the attenuation parameters, the backscattering, et cetera, and I can then invert all of those things to produce data that is more photoconsistent, that looks as if it were taken in air, in some new environment in which I have never been before, but I only have data that I'm gathering online. And so again, so we did some experiments with this. We set up our camera system. We had some artificial rock platforms and tested it. And at the end of the day, this is what almost all your underwater images look like. Typically, this is what you can do sort of with a generative network. And there's nothing inherently, like, this looks OK. You can achieve similar results if you sort of hack around it and basically do histogram equalization. The one benefit of this is it ends up being consistent over depths. So that means I can be shallow, I can be deep. Where histogram equalization would produce different results. Approaches like this are more photoconsistent, so they aid with 3D reconstruction, SLAM, whatever other tasks you want. If you guys have any questions as I'm going, please don't hesitate to let me know. OK, great. OK, so switching gears, again, talking about ways of getting out of having to actually label any data. We've been thinking about what other things do motion afford you that allow you to kind of save time and be able to learn things without having to do anything. So this is a graduate student that's probably a year away from graduation, one of his recent papers. But you have my robot driving around. And my robot's driving around, and I showed you that image earlier where we were getting single-shot detections. We were detecting cars, we were detecting buses, whatever, but we weren't always getting it right. And the first thing, if you talk to somebody that deploys vehicles, they say, well, we'll put a tracker on top of that. And that's the easiest way of kind of eliminating this problem, this noise that you see in single shot detectors. And that actually works super well. So when you're modern deployed AV, you have a single shot detector, and then you typically have a tracker on top of that that uses additional information to figure out where things are. And one of the things that came to one of my graduate students was that, OK, well, I have this really rich information of where this vehicle is over a long period of time, and I know I have a single shot detector that I can run on that. And so I now have the ability to detect when my single shot detector failed, but my tracker said there was an object there. And if you look and you run that forward and you run that backward in time, you can end up with all of the places where your single shot detector failed, but you know that there's still a car there. Or at least you know there's a partially occluded car or something else happened that made your single shot detector fail. So what he ended up doing is then he would run his detector, he would run his tracker, he would pose this as a binary classification problem. Is this a real false positive or a real false negative? And you do the same thing with stereo, right? So if I have a left image and a right image from a stereo pair, if I see a thing in the left image and I have a depth map, I know precisely where that thing should be in the right image, right? And for a car, something as big as a car or a person, really just the sort of, even if you're coarsely aware of their depth, that's enough to project to the other image correctly. And so if I run my single shot detector on my left image and my right image and I don't get the same thing, or I don't get the shift of that in the right way, that tells me again that I probably am missing a thing. Now, when he posed this to me, I said, look, I don't think this is going to work because you're only going to get a few examples. It's mostly going to be correct, and you're going to find a few corner cases. And I ended up being proven wrong. And then one of the other cool things is they were able to implement this. So we work with Ford, and they were able to implement this on a much larger fleet. Or we're working to implement this on a much larger fleet level so that you could have this running on any car that was out there taking data. Because again, it comes for free because all it really requires is a detector and a tracker or stereo estimation, which you're doing anyway. So what he started pulling out was with sort of the detectors du jour of the day, all the examples of things that were missed with free labels that came from projecting the bounding box forward in time through either using the stereo or temporally. And you end up with all of basically every example of why using only passive sensing is going to be terrifying because tons of things cause it to fail. So we ended up with thousands of examples of oversaturation causing failure, of shadowing causing failure, of occlusion causing failure. And even some examples where it should just be getting it right, not clear why it's getting that one wrong or that one wrong or that one wrong. So there's some more. We ran this on Kitty and Oxford Robocar and a bunch of others. These are the stereo cues. We ran it on the simulated data, which was a much larger data set. But let me see. This should hopefully show you. So if you're watching a single shot detector, which is your SSD, please.
So you're using your tracker to provide supervision. Do you ever worry about your tracker having failures and then having mislabeled in your basic supervision? So how do you deal with that?
Yeah, no, great question. So one of the challenges here is you have to make that binary classification problem. You say, should I accept this label? Very aggressive, right? Because it's better to throw away. You can run this as long as you want. And so there are examples in which exactly, you move along the precision recall curve until you're taking only data that you're pretty confident in. But even this alone was able to produce, on a bunch of data sets trained on sort of, Kitty, which is arguably fairly state-of-the-art for, it used to be kind of state-of-the-art for what we were doing. So what you'll see here are actual detections. All the green boxes are temporal errors, and the blue boxes are going to be stereo errors. That's a little hard to see. Maybe this one will be easier. So there's a ton that you miss as you're driving around. So if you just run on this, you'll see that kind of small cars that are partially occluded, and you end up getting tens of labels per every sort of minute of frame, which to me was more scary that our object detectors are missing tons of stuff rather than this being incredibly. Anyways, question, please.
Do you do any work to understand what features the detectors were picking up that would cause you to miss these?
Yeah, so it ended up being kind of everything that we know to be problematic. So it is changes in illumination, loss of texture, rapid shifts in color, really all the things that make sort of the corner cases of object detection in imagery hard. So sort of where he's going with this, or sort of what the next steps are incorporating this back into a learning framework to iteratively get better, but using the labels that you know to be noisier than the labels that you would get from a human. And so there's lots of work happening in sort of the ML community to deal with noisy labels, incomplete labels, all of that. So the hope is that as that, it ends up being that's also a really hard independent research problem. And as that gets better, hopefully, approaches like this. I think the most useful version of this is really at a fleet level as opposed to on any individual vehicle, because you can be gathering all of the corner cases across many vehicles, and then you're talking about tens of thousands of labels as opposed to sort of order of thousands, even over the data sets that we have. OK, so sort of one of the other kind of angles here in terms of thinking about physics is trying to apply physical constraints to problems like tracking human beings or figuring out where they are in the world. So this is a data set that we gathered at intersections at Ann Arbor. So there's a four-way stop, and we were particularly interested from an autonomous vehicle perspective about figuring out sort of what human behavior is at a four-way stop. How do I know that someone's indicating they're going to cross, what their body language is, all the kind of things that make it easy for a human being to do that, but hard for a autonomous vehicle to do it. So sort of in strict contrast to everything I've been saying, we ended up having to human label a lot of this, which ended up being really, really, really annoying. And so we started out with that premise that we were going to human label lots of it. And then, in fact, what we did is we moved away from that because it was costing like tens of thousands of dollars to get hundreds of or maybe 1,000, 2,000 frames labeled with the kind of fidelity we wanted, which was human skeletons, pixel-wise segmentations, et cetera. And so then what one of my graduate students started to develop was taking lots of the work that's been done in body pose fitting and body model fitting and using the additional data that we have from an AV. So in this case, LiDAR data, and fusing the LiDAR data, the stereo data, and the image data together to extract 3D body pose models of human beings. And so really what this was a bootstrapping of a labeling task for a data set where if I started with some course information, let's say like bounding boxes of where the people are, and I take the LiDAR data and I put it in to one of these body fitting models, I can end up with both skeletal information, pixelized information, but ultimately we're interested in 3D body pose information. And so the goal of sort of both that data set and then sort of what I'll show you in terms of what we're doing in prediction is predicting full up 3D body pose models from human beings, and not in sort of the canonical examples, which are in a backgroundless room or with Kinect data indoors or even up close. You can see sort of where modern computer vision is. They can tell my skeleton for images that are near, but at sort of ranges that would be useful for autonomous vehicles, so 30 or 40 meters out. And so what we began to do is capture lots of variability in what humans were doing. They were carrying things, holding hands, carrying bags, talking on cell phones, moving through intersections. And then we got even more complicated ones. So we got into trying fitting body pose models on cycling, wheelchairs, dismounting bikes, running, et cetera. And so what you're seeing here, these are the end results of us using the LiDAR data, the camera data, the stereo data to fit body pose models across a variety of pedestrians in different positions and under fairly heavy occlusion. Where this is heading, or what our goal was not just to figure out where they are now, but obviously to figure out where they're going to be. And so thinking about the prediction of body pose models over a number of steps. And so our initial attempts of that were sort of in the skeletal phase, where we're just trying to figure out sort of where we think the key points of the person are going to be. And it turns out doing that in 3D works very, very poorly. So you can see these really great demos of sort of where the state of the art is in 2D body pose detection. If I take that out even sort of 5, 10 meters away from where I am, the 3D positions of them become wildly inaccurate. So it's a little hard to see here, but they can be up to like a meter off in Z, sometimes even in X and Y. So what we started to move to was not skeletal positions, but again, these full 3D meshes we wanted to predict. And again, that gives you a lot more rich information because we have the whole disparity map of what we're seeing from the stereo. And you can get away with sort of things so you can eliminate things that would be inherently problematic with just the key point estimation by thinking about this entire one that is kinematically rigged in such a way that your body can only move in the ways that your body can move. And so what we got really focused on is thinking about fitting these kinematic body models to where people were in 3D space. And then thinking about making predictions by thinking about how that's going to move through time and sort of how that body model obviously can't occlude itself, it can't run into itself, and thinking about how that full 3D motion of the person is going to move over a period of time. We wanted to include things we knew from physics, so things like support. And so we looked at sort of where the foot placement would be and all the things that we do in legged robots to figure out stability and how the person and how a legged robot isn't going to fall over are also useful for predicting where a body pose is going to be. And so we would calculate the envelope of support. We would also look at some ideas of symmetry of the body from where that comes. Sort of how your limbs are typically oriented as you're walking, what those periods look like, and all the things that people in kinematics, or sorry, in sort of whatever body pose estimation for human beings have figured out. And then if you throw all of that sort of parameterization at sort of the same tools that are now really, really popular, like LSTMs, other things like that, you end up with results that look reasonably credible and work typically better than what you would end up with if you're just using the raw perception data to estimate the pose. So hopefully this will show you that. And so again, we were focused on thinking about people at far ends of intersections and like sort of where this would be. So the car is positioned just out of frame. And the second thing we're interested in is doing for large groups of pedestrians. So not just for one person, but thinking about everybody and their global position with respect to where the vehicle is. So what you'll see here is the vehicle's here. There's a spinning mirror LiDAR, a set of stereo cameras, and for this, the vehicle was stationary. But we're trying to estimate the full 3D pose of all the pedestrians in the scene. So we had 4 Velodynes, 2 stereo cameras. And again, looking at the periodicity of the human gait, and so thinking about what we can predict in terms of step after step, thinking about all the symmetry that would happen in the limbs in both in-plane and side plane, thinking about the ground contact between the foot and the ground. And so this is on that PEDX data set, our prediction results. And so these were the initial training labels. And then you'll see these for groups of pedestrians moving in state. So they look a little crazy. But I promise you, if you look at the raw data from just what you'd get out of sort of your kind of standard prediction algorithm, it looks much worse. And so this is sort of what some baseline approaches look like, just doing single shot versus where the person actually went. So the red is the ground truth, the blue is sort of a much simpler baseline. And as you get further out, you get worse and worse, but like you end up with a motion that to some degree would be enough to act on, I would argue, at least for a couple of seconds in the future from your self-driving car. So we would try in real intersections to look at sort of what this would actually look like. You end up, for the most part, getting the things that I think would be critical to understand, like holding a phone, holding coffee, those kind of things. That is one of our engineers. I don't know why we blurred his face, but him moving around. And then someone walking a bike again. OK. A bunch more of that. I don't know why this is here. OK. No, these are supposed to be skipped. OK. I'll go back to them. So one of the kind of last things I want to tell you about is the idea of thinking about self-supervision just from one set of data. So this is not across data. This is leveraging the relationship between semantics and sort of estimation of disparity to figure out better disparity maps and then also better semantic segmentation maps. So if I have a left image and a right image and a sparse depth map, and that can come from LiDAR, that can come from other sources, what we're doing is passing that all into a network. So this is probably the most traditional computer vision-y thing that I will show you, and then ending up over here with a dense depth map that upsamples whatever this input depth map is with the stereo information. And look, there's a huge range of this being done in the computer vision community. What I think we in robotics probably have an edge on is lots and lots of it is being done with a single modality and almost exclusively with monocular imagery. And so I think there are huge gains to be had looking at stereo data, which obviously in robotics we have a really great familiarity with, that just isn't being used really, really heavily. And so these are upsamplings of sparse point clouds to get full and complete depth maps, and it's a little hard to see at this resolution, but you end up getting complete cars, full people, telephone poles, all that kind of fun stuff. And if you look at the error maps, you end up with much, much lower error than you would with either just the LiDAR data or the stereo data. And particularly at long ranges, that end up being a big win from that perspective. I think the other important thing that we took away from sort of these ideas was that you can have really, really sparse amounts of LiDAR data and still end up with really, really high quality results. And so there's this big push in self-driving cars to have more expensive lasers at every kind of step. And so we have 16 beam lasers and then 64 beam lasers, and now you can buy a 128 beam laser for $70,000. And with just one camera, and particularly with two cameras, we were sampling down to basically the equivalent of an 8-beam Velodyne and seeing performances that were very, very similar to what you would see with the 128 beam. So again, you get these wins if you kind of avoid thinking about using all of that. OK, the last thing I will tell you about is me and every other joker in the world now as a startup. And so because I got really frustrated with everything not working in full-size self-driving cars, we started building really small and lightweight vehicles. And so this is about 100 pounds. It travels about 15 miles an hour. And so what we're trying to do is push a lot of the same autonomous technology that we think is going to work at some point eventually for full-size cars, but maybe not anytime soon. And just make it a lot easier by going a lot slower. And so the stoppiness of this vehicle is about 5 feet. And so you can end up messing up a lot more often. And it's really light. I've been hit by it several times. It's totally fine. And so we're targeting food delivery as one of the early applications. But I was having a conversation with John Leonard earlier, and we were just talking about how it's not when full autonomy is going to get here, but it's sort of in what forms. And I think the forms that make it easier, like particularly going slower and being lighter and all of that fun stuff, make that a lot easier. So we got this video produced very expensively, so I will zoom through it. But at the end of the day, I think we've come so far in self-driving and in a lot of other kind of ways in robotics. And I think to get to market, we just need to make the problems we're solving simpler. These are paid actors. I don't know these people. They were very nice. They came at high cost. They look like they're very excited to receive their food. Yeah. OK. I think that's it. Thanks, guys.
Thank you very much.
No
Any questions?
Thank you. Fantastic talk. Thank you so much. One question I have is in regards to kind of like this idea of using synthetic data is becoming so prevalent. What is kind of your insight on what kind of features are very hard to estimate from it, and which one it does really well estimating? Do you have any insight?
Yeah, so I think the things that we found worked really well, particularly from the photorealistic simulators. Cars work much better than people. People work pretty poorly. Cars are certainly the best. Things that are big and metal, like we know how to render really accurately, and so like that's probably the first thing. So artificial, man-made things are probably the starting place. The thing that is, I guess, most difficult that we found and sort of where most of our efforts are going now is that networks are really good at keying in on things that you don't care about or not visually salient to you as a person, but the network, you say, hey, here's a bunch of data, figure out what matters in this, and that's great, and that's like taking us a long way from where we were when we were hand designing features, but that also means that you can key in on features that are completely unimportant. And so probably the most distracting thing is that there are rendering artifacts or things that are produced in artificial data that just don't exist in real data, and the sort of distributions of error do not look like they do in real data. And so what often will happen if you don't regularize whatever your training process is, either with real data or thinking about other ways of regularizing it, you end up with it keying in on rendering artifacts to figure out what is a car, which is not useful when you go out in the real world and there are no rendering artifacts. So that is probably what I would argue is one of the biggest challenges for outdoor sort of self-drivey rendery things, if that helps. Yeah.
Thanks.
No worries. I can hear you, I'm sure. Oh, wait, I guess it's for the video or something, right?
Thanks, I really enjoyed the talk. So I guess my question is about what can you learn self-supervised versus what do you need human labels for? So, you know, geometry information, all the stereo stuff makes a lot of sense to learn self-supervised, but if you just don't know what a car is and that's a human thing.
Yep.
So are there ways to sort of still self-supervise that, like learn classes and then I'll label them, you know, on the back end, or do we have to use sim to real? So sort of for those more semantic things, is there any way to avoid at least some amount of human labeling?
You know, I mean, that's the thing that we try to think a lot about. We wanted to see if we could bootstrap off either self-supervised or something else to get to the point. So I'm of two minds of this, right? I think there's some really interesting research questions that could be asked about how you would fundamentally go about, with no knowledge of the world, beginning to categorize things. And there's actually a lot of work happening in machine learning to do exactly that, right? So if I just have completely unlabeled data and I want to label it into categories, but it goes back to that problem I was just highlighting. There are many things in there that may be salient in the data that are irrelevant for the semantic meaning that we would apply to it. I would say, at least the pragmatist in me, is we're in a world now where ImageNet exists, right? And so the notion that you can bootstrap to some degree to get you to a place where man-made objects are recognizable at a reasonable enough rate that you can begin to play games with getting to that kind of long tail. So we have not spent a bunch of research time thinking about the thing where you know nothing about the world, simply because there are such abundant sources of small amounts of labeled data. I think there's probably lots to be done there. We've sort of just shifted to focus on this idea of domain adaptation. So if I have data from some labeled data from some world that somebody has already spent the time to gather, and I have a new camera system, different camera setup, different environment, different lighting, how do I adapt to that? But I think to some degree, somebody should be looking at whether or not we even need any labels, right? Because it doesn't feel like that is, okay. Okay. Hope that answers that. Anything else? Yeah.
Wait, what? 1 second.
So you mentioned about the performance reaching an asymptote when you're training in the simulators, right? I mean, how much do you think that is because of the diversity issue?
Yeah.
Or is it the fundamental algorithm? Is it the diversity? I mean, if you have more diversity in your simulators, would it kind of match up?
Yeah, so I think it is diversity in the simulator, almost certainly. I think there's an asymptote probably to some of the approaches, but I'm not sure that we had hit. I mean, if you think about your modern neural net as 100 million, 200 million parameters, there's a lot of room in there to learn stuff. If you talk to, so I mean, we are poor and lowly academic researchers. If you talk to people within some of the larger self-driving outfits, they will tell you the sizes of some of their labeled data sets, and they are orders of magnitude bigger than what we're working with, right? So we're putzing around with Kitty, 7,000 images. Inside like Uber and others, you're talking data sets of a couple million to even more for some problems, right? And so, and they say that there's obviously value. They didn't spend, whatever, N million dollars to label 10 million images for no reason. So there's value in continuing. So what we hit was the asymptote just in the variety of the simulator. To your point, the simulators have hit a limit, and there isn't enough sophistication or enough variability or enough photorealism to capture the error distributions that exist in the real world. And so that is still the gap. And but you talk to them, they spent N million dollars labeling 10 million images, and one of the real bummers is that if you change out that camera system, that 10 million images is great, it gets you 98% on that data set. You change the camera system out, you even change the environment you're running in, and it doesn't drop to nothing, right? It still works, right? That's why ImageNet works when we run it on our data, but it drops to 90 or something that is well below the asymptote, like the long tail you need to get to. So better simulators, but probably better ways of adapting that domain to the real domain. It would be the two things I would say.
I mean, so I guess it always comes down to like better simulators or more content creators who can contain richer content, right? I mean, those are
right.
two.
Well, and that's the other piece, right? Yeah. So the reason that GTA works so much better than I think some of the other ones is that the assets in, like the rendering engine, they're all, Unreal Engine, they're all sort of comparable to some degree. The assets in GTA are much better. They spent, I don't know, $100 million making that game. I think it's the highest selling media property of all time. That's why they didn't want to talk to us. They made like $1 billion. Like literally, I think they sold like, I don't know, like they made literally $1 billion or like $10 billion or something. So like, it's like, oh, hey, come jack around with our little academic research projects. I don't care about that, right? They're selling copies of the game. But the assets were so much richer. But then are we just trading human labelers for underpaid 3D artists that sit in some room and make 3D assets all day? That doesn't seem like the future either, right? So I don't know.
Any questions?
So on the slide, you quickly showed that you had something like 2 million synthetic images. Are you ever worried about overfitting to your synthetic data set versus your real data set? And also, what is the ratio of synthetic images to real?
So all that data was all the results there were complete sim. So there's been a lot of work with balanced sim and real data sets. And so the goal of that paper was to show with no real data what you could get to. Yes, overfitting is a huge problem. That's where that asymptote came in. And in fact, you begin to see performance decrease, right? So to that earlier point, like there isn't enough variety in the simulator to really facilitate continued gains after some point. But all of those results were 2 million simulated images, 0 real images. If you put real images in, the performance goes up. But that's only if you put in real images from the domain you're looking at. So if you put in real kitty images, it helps. If you put in real cityscapes images, no. Please. Just yell, yeah.
I'm assuming you're testing on real data, right?
That's right. It's all real data. Yep.
How can humans learn from so few examples?
Well, that's a great question, John.
We can stop there.
I don't know if I have a good answer to that. I think ultimately this highlights, I think, the problem we have in lots of these things, right? I don't think we have a great model for why we're so much better at these tasks with so much fewer examples, right? Like it gets to the generalization, our ability to generalize, they just don't exist in these systems. And the brittleness of these systems is their inability to generalize. And if I change cameras and it doesn't work, it suggests how ultimately fragile supervised learning is for solving some of these things. So,
I think it's the perfect question to transition to the reception on the other side of this room. There's food and drinks, and maybe we can find the answer.
Thank you for inviting me.
Thanks,
everybody.